So today we're going to be looking at the history of the atmosphere. So we're going to be looking at how the Earth's early atmosphere formed and the intense volcanic action kind of theory for its formation. We're going to have a look at how oxygen was formed, about the processes that led to the formation of oxygen and why the levels of oxygen increased over time. And then we're going to do the same for carbon dioxide to look at where it came from, look at how its levels have changed over time and why, and we're going to link those to some specific processes as well. So first job is in your books. I want you to write down the word and balance symbol equation for photosynthesis, and I would like you to explain the importance of this chemical reaction for life on Earth. Okay, so hopefully we've got carbon dioxide plus water reacts to form oxygen and glucose, and of course formula-wise 6CO2 plus 6H2O goes to form 6O2 and C6H12O6, and we can have a light above the arrow, and we can also consider having chlorophyll as well. Chlorophyll as well, not chloroform. So reasons why it's important. First thing that we'd want to think about is the fact that the reaction is producing glucose, which is food for the organism itself, but then also it provides food for organisms that eat it. And so when we look at food chains, most food chains start with a photosynthetic organism. The second thing, which we wouldn't necessarily consider, would be about the oxygen that's produced, and of course the oxygen is a waste product, and other organisms will use that in respiration in order to release energy from glucose, which they'll use to drive other processes. So the first thing for us to consider is what is an atmosphere, and so we want to consider about the fact that the Earth is relatively unique in that it does have an atmosphere, and particularly unique in the fact that that atmosphere is able to support life. So an atmosphere is essentially an envelope of gases which surround a planet. So you can see in this image we've got the troposphere, which is within the first 15 kilometers of Earth, and then we've got the stratosphere above that. Now, when we're talking about gases within that first 15 kilometers, 80% of the atmospheric gases are within there. So we can see that they're relatively dense, which means across the next kind of going up to 55 kilometers, that stratosphere, it's only got 20% of the gases, which is not very much when we consider compared what's in the troposphere. And overall, it's a very, very thin layer in which life exists. So the atmosphere for the past 200 million years has stayed pretty fixed, pretty constant. The proportions haven't really changed. And so those proportions are about 4/5 of the atmosphere, roughly 80% is nitrogen. The other remaining fifth is oxygen. And there is a tiny amount of various other gases, including carbon dioxide, water vapor, and argon. Now, that hasn't always been the case, as we're going to see as we look at the early Earth's atmosphere. Now, you're going to need to make some notes on this side, please. So the early atmosphere was very, very different, and we're going to look at one of the theories that explains the process of how that atmosphere actually formed. So there's a number of different theories, and the reason that there are a number of different ones rather than being one definitive one is because we're talking about going back 4.6 billion years, which is a huge distance, and as a consequence we don't have very much evidence left around today. So the theory that you need to know about is the volcanic theory, and so the idea is that during the first billion years or so of the Earth's existence there was really intense volcanic activity, and so what was associated with that volcanic activity was a release of gases, particularly water vapour. So it was a large amount of water vapour that was released, and that water vapour condensed and it formed the oceans as we see them today. Now, the main gas that would have been released at this period would have been carbon dioxide, and there would have been very, very little oxygen within the atmosphere at that stage, which means that the atmosphere probably would have been really hot. It would have, because carbon dioxide would be trapping lots of the sun's radiation in, so it would have like a super greenhouse effect. And so a way of thinking about it would be being quite similar to perhaps Venus's atmosphere, which is very hot, or potentially Mars' atmosphere, which a bit further away from the sun, so it's a bit colder. But very inhospitable. So here's some current data on Venus's atmosphere. So you can see temperature, you can see percentages of various gases. And so the first thing that we want to consider is, based on that data, how much carbon dioxide and argon would you expect the Earth's early atmosphere to have? Okay, so carbon dioxide based on that should have been something like 96%, which is very different from today's values of 0.04%, and argon would be less than 1%, which is quite similar to the amount that we have in our current atmosphere. So our next question is, well, why does Venus have no oceans, or ocean singular? And of course you should be looking at the fact that there's very little water vapour present in the atmosphere, so there would have been very little available to condense and form those oceans. So other gases that would have been produced by volcano would have been nitrogen, and over time that would have gradually built up to get up to those levels of about the 4/5 that we have today, so 78%. We would have also had the production of small amounts of alkanes, so methane being produced here. And you would have also expected some ammonia to be produced as well because of those conditions that are there. The carbon dioxide that was produced will have dissolved in the water in the ocean, and in dissolving in the water in the ocean it will have formed carbonates, and so those carbonates, some of them will be insoluble in water, and so what happens is they precipitate out, so they form this solid which you can see in this diagram down here, and that solid ends up being suspended. Now the problem is that over time that suspension will end up sedimenting out, and so we'll end up with a layer of precipitate or a layer of sediment being left at the bottom, and so this is what happens at the bottom of the ocean. This dissolving carbon dioxide into water would have reduced CO2 levels in the air. So oxygen-wise, we would be talking about oxygen being produced first of all about 2.7 billion years ago with the appearance of algae and plants. So at that point they would have started photosynthesizing, and photosynthesis would have produced oxygen, and that oxygen would end up in the atmosphere. So just a reminder of that photosynthesis equation again. And as we end up with more plants evolving and plants getting more complex and more able to carry out more photosynthesis, then what we would find is that the percentage of carbon dioxide would be decreasing and the percentage of oxygen would be increasing. So we've got two processes that we've looked at so far, the dissolving of CO2 and the process of photosynthesis. That would be reducing the amount of carbon dioxide in the air, and then we've got this process here which would be increasing percentage of oxygen. And of course as soon as we get oxygen being produced, that means that we're able to get organisms that need oxygen to survive, that need oxygen for aerobic respiration, and so those organisms will end up arriving, evolving and surviving within this atmosphere, and again contributing to changes within that atmosphere. Having explained about why the concentration of oxygen has increased in the atmosphere due to the action of photosynthesis in algae and plants, we need to consider about why that percentage of carbon dioxide has decreased. Remember, when we were looking at that data, that was based around Venus's atmosphere, we're talking about that the volcanoes potentially were pumping out something like 96% of the atmosphere being carbon dioxide. And obviously we're not at those levels now, because as I mentioned previously, we're talking about that CO2 levels are around 0.04%. So what we need to work out is, where is that carbon dioxide gone? So have a think about that. And things that we should be considering are kind of three processes overall. The first is the action of photosynthesis again. Now, we know that photosynthesis produces oxygen as a waste product, and so that's led to the increasing concentration of oxygen in the atmosphere. But what we also have is that, of course, that photosynthesis uses up carbon dioxide, so that will reduce the levels of CO2 in the atmosphere. The second is the formation of sedimentary rocks, and so there we're particularly thinking about carbonate-based rocks like limestone, which is made up of calcium carbonate. And the final one is the formation of fossil fuels that contain carbon. Now, all of these processes, particularly the fossil fuel one, is one of the reasons why we begin to get concerned about locking up carbon that's been out of the carbon cycle for a number of years, or for millions of years in fact, because we're talking about huge amounts of CO2 being locked up in these different reserves, particularly within the fossil fuel reserve. So we're going to work our way in a little bit more detail through these. So a little bit of a reminder about limestone formation. So limestone is formed from calcium carbonate, and so there are two sources for that calcium carbonate. The first one is the shells and bones of marine organisms. And the point is that as these organisms died, particularly their shells end up falling down to the ocean floor as sediment, and layers of that build up over time. The second way in which we have it is what we looked at earlier, about where calcium carbonate isn't soluble, and so we have that it forms a precipitate when there's that reaction to produce it in water, and so that sediment, that precipitate, that solid that is suspended within the ocean, will end up falling out of the ocean and being deposited at the bottom of the ocean on the floor. Over time, we end up with those layers building up, as we can see in this diagram over on the right hand side, these layers of rock that are building up, and those layers of rock end up putting pressure on the layers below, and so we end up with, first of all, compaction, and then the minerals in between them, we end up with cementation, so that we end up with overall sedimentary rock being formed like these limestone cliffs that we can see in this image. Formation of fossil fuels. Again, this should be a little bit of a reminder, really. Really, we're thinking here about the remains of dead organisms from millions of years ago that go through this special kind of process and lead to the production of fossil fuels. So with oil and gas, we're thinking about dead marine organisms. So we're thinking about things like squid and plankton and phytoplankton and things like that, that end up dying, being covered up on the ocean floor by silt and sand and some of that sediment, and over time we get lots of heat and pressure acting upon those materials, those remains that are left behind, and we end up with oil and gas being formed. And so we can see that represented in this diagram over here. And of course those oil and gas gets trapped in these rock layers, these sedimentary rock layers, and we drill down in order to release those deposits. Coal is formed in a slightly different way. It's a dead plant material, but then it's, again, we're thinking about layers, we're thinking about the action of heat and pressure that ends up changing that material, that carbon-rich material, into that rock that we recognise as being coal. So our final bit for you to consider is a series of questions here. So I've got 3 questions with answers that I would like you to have a go at. So here's the first one. So here I hope you'd be thinking about the intense volcanic activity, large amounts of CO2 being released along with water vapour, which condenses to form oceans. Then we get nitrogen being produced in smaller amounts, but it builds up over time because it's not used up, and very small amounts of methane and ammonia. Second question. So different factors have affected the Earth's atmosphere since formation. Identify 4 factors that have decreased levels of CO2. So here I would be hoping you picked up increased photosynthesis levels by plants and algae, carbon dioxide dissolving in oceans, that carbon dioxide reacting and forming calcium carbonate, and so we get the sedimentation of both that and the calcium carbonate that's locked up in marine organism shells in order to fill limestone, and then of course the formation of fossil fuels. So this one, identify factors that increase the levels of oxygen. So here we'd want to be thinking about, here is some algae in this image that we've got here, and photosynthesis occurring in those organisms, which of course takes in the carbon dioxide, lowering the levels of that, and releases oxygen, which increases the levels of that. Okay, there's some work set to go along with this, a little bit of a worksheet to have a look at, a few questions, and you'll need to go through and make notes on this presentation if you haven't done already. Right, thanks a lot, and I will catch up with you in a live lesson sometime soon. Bye-bye.